Hello everyone, I'm Na Meng, an assistant professor from Virginia Tech. Today, I'd like to present our work on how execution information helps with information retrieval-based bug localization. This is a collaborative project with my prior student Tang Dao and my collaborator Lingming Zhang from UT Dallas. Bug localization is important in software maintenance because effective bug fixing relies on the precise bug location information. However, bug localization is challenging and time-consuming. Given a bug report, developers may spend tremendous time understanding the report together with the code in order to locate bugs. Various approaches have been proposed to help localize bugs. For instance, information retrieval-based bug localization considers buggy programs as plain documents, extracts words from the documents, and then indexes the software entities like classes and methods with those words. Meanwhile, it treats every bug report as a query to the indexed documents in order to retrieve and rank a list of software entities based on their relevance or similarity to the query. Such approaches mainly leverage the static information relevant to bugs. Another kind of techniques is spectrum-based bug localization. Given a buggy program and a set of test cases, including pass and fail tests, spectrum-based bug localization executes the program with all the test cases in order to collect the execution information of each passed or failed test and to calculate the suspicious score of every location so that it can rank the code locations based on the scores. So such techniques mainly leverage dynamic information relevant to bugs. So given the existing approaches which either leverage static or dynamic information, we are curious whether it is possible to combine these two kinds of information together in order to improve bug localization. Therefore, in our research, we investigated the following research question. By combining static and dynamic information, can we improve bug localization? To answer this question, we have systematically investigated different ways to combine static and dynamic information. To make our empirical study well representative, we have experimented with 3 different IR-based techniques, like baseline, BugLocator, and BLUiR. We have collected 3 kinds of execution information, including coverage, slicing, and spectrum. Especially, in order to collect the spectrum information, we found various ways defined to calculate the suspicious scores for code locations. Therefore, we included 4 popular ways to calculate spectrum information, such as tarantula, OCI, Jacquard, and Ample. And we have designed and implemented 4 ways of combining the 2 kinds of information, including IRC, IRS, IRCP, and IRSP. In the following several slides, I will provide more details to explain the design and the meaning of these different 4 ways. So we have collected 3 types of execution information in our investigation. So to collect the coverage information, we instrumented methods and recorded classes or methods executed by the fail test. To collect the slicing information, we instrumented methods and recorded executed classes or methods relevant to a failure. Compared with coverage, slicing includes a subset of the executed classes and methods which have either control or data dependency relations with the failure statement. We also collected the spectrum information. To collect the spectrum, we instrumented methods and calculated the suspiciousness of each executed class or method. Different from coverage and slicing, spectrum takes into account not only the execution information of failed tests, but also the execution information of past tests. We have designed different combination ways based on two strategies. First, search space reduction. We can use the coverage or slicing information of failed tests to refine the IR-based bug localization results. And the intuition is if a code location is never executed or covered by a failed test, it shouldn't be included into the IR-based bug localization results because it is very unlikely to cause the bug. And the second strategy is rank tuning. We use the rank list of spectrum information to improve the ranking of IR-based bug localization results. And the intuition here is that if two code locations have similar ranks, and suppose one of the code locations are executed by more failed tests, it should be ranked higher, much higher than the other. With more details, so for the search space reduction strategy, suppose we use N to represent the original IR-based bug localization result, and M represent the locations which are not covered by any failed test. So by removing these irrelevant locations which haven't been covered by any failed test, we can effectively refine the original IR-based rank list. Because if code locations are not executed by failed tests, they shouldn't be responsible to the bug or the failure. Based on this strategy, we have designed and implemented IRC and IRS. So with IRC, we use the coverage information to refine the IR-based bug localization results. With IRS, we use the slicing information to refine the IR-based bug localization results. So the second strategy is rank tuning. Since the IR-based techniques produce one rank list, while spectrum-based techniques produce another rank list, we tune the ranks by merging these two lists together using the following formula. So in this formula, score DQ represents the score produced by an IR-based bug localization technique, while susp-D is the score computed by the spectrum-based bug localization techniques. And we defined a parameter alpha to control the weights of these two scores when computing or when creating an adjusted score called score prime DQ. We have no prior knowledge about the best setting of alpha. So in our experiment, we experimented by changing alpha between 0 and 1 with 0.1 increment in order to investigate the best setting. Based on this strategy, we have designed and implemented another two combination ways, IRCP and IRSP. IRCP means that we first use the coverage information to refine the IR-based results, and then combine the refined list with spectrum information. IRSP means that we first use the slicing information to refine the IR-based rank list, and then combine the refined list with spectrum information. So we conducted our experiments using the existing benchmark suite published by BLUiR et al. In the benchmark, there are 157 real bug examples from 4 open source projects, AspectJ, and Lucene, and Rhino. So For each example, this dataset contains one bug report, one buggy program, the fixed version of the buggy program, and a set of test cases, including passed and failed tests. According to the table, you can see that some of the bugs may correspond to single bug locations, while some of them correspond to multiple locations. So here are the results we have got. We first compared IR and IRC at both class level and method level. So with the class level bug localization, we tried to locate the class which contains the bug. And for the method level bug localization, we tried to identify the method which contains the bug. Generally speaking, method level bug localization is more challenging than class level bug localization because there are many more methods than classes, and the body of the method is smaller than the body, usually smaller than the body of class. So we experimented with 3 different IR-based techniques. Under each technique, there are 2 columns. The IR column corresponds to the bug localization results by the original IR-based technique, while IRC corresponds to the results due to the refined ranked list using coverage. And we measure the effectiveness of different techniques using the popular or well-defined metrics like top 1, top 5, top 10, MAP, and MRR. For example, so top 1, top 5, top 10 basically means that among the top N locations, how many of them are the actual buggy locations? And MAP and MRR are also widely used metrics to measure the effectiveness of IR-based bug localization techniques. So based on this table, we observe that at the class level, coverage consistently improved all studied IR-based techniques. That is reasonable because it effectively removed irrelevant method locations or irrelevant classes locations. At a class level, at method level, the coverage improved IR-based bug localization more significantly than at class level. We also compared IRC and IRS, since slicing information only includes a subset of the information included by coverage. So we anticipate it to improve the IR-based results more significantly than IRC. And as expected, we observed that slicing was more helpful than coverage in improving IR-based techniques. We also did comparison between IRC and IRCP, and the main difference between these 2 strategies is that the second one combined the ranked list with spectrum information to tune the relative ranks between the code locations. And we just put part of the experiment results here. For more details, please read our paper. So, based on the comparison experiments, we observed that spectrum information was effective to improve IRC at method level instead of at class level. With tarantula and alpha equal to 0.7, IRCP almost always achieved the best performance. We also did a similar comparison between IRS and IRSP. And we found that the spectrum information was also effective to improve IRP at the method level instead of at class level. So, and other similar findings to what we have observed for the IRC versus IRCP. Finally, we compared our combination approaches with AML, the state-of-the-art hybrid approach which combines an IR-based bug localization technique and a spectrum-based bug localization technique. There are mainly two differences between our research and AML. First, AML contains a very complicated algorithm to combine the two kinds of information. However, in our research, we mainly focus on the simple ways to combine information. And second, AML only investigated one IR-based bug localization technique and one spectrum technique. However, in our empirical study, we tried different IR-based techniques and collected different kinds of execution information to see whether execution information can generally help with bug localization or the combination approach itself plays the trick. And based on our comparison, IRC outperformed AML in all metrics but one. IRCP outperformed AML. In this comparison, although we didn't include IRS and IRSP, it is reasonable to expect both of these approaches can work better than IRC, because slicing information is always more effective than coverage information to refine the rank list. To conclude, we observe that various execution information can effectively help with IR-based bug localization, even though the combination approaches are simple and easy to understand. With search space reduction strategy, we can remove irrelevant code locations from the IR-based list and improve the ranking of actual buggy locations. With rank tuning, we can improve the ranking of actual buggy locations that are covered by many failed tests. So, in our experiments, we also realized that we need to investigate more approaches to handle hard-to-find bugs in future. For example, all these investigated techniques still do not work well when bug location information is not mentioned in the bug report. And in some cases, even though the actual bug location is mentioned in the bug report, there are still a lot of irrelevant code locations explicitly mentioned in the same bug report. And the current approaches cannot always effectively identify the bug location because the actual bug location is buried with a lot of noisy location information. So, in future, we plan to investigate some more advanced techniques in order to handle those cases. So this concludes my talk. Thank you for your attention. Do you have any questions?